All right, so I'm going to spend a little bit of time here looking at some of the solutions to vector subtraction. Now this first one here, the initial position of an automobile is at 30 kilometers east of Dauphin. Let's just put a little mark here. Here's Dauphin. 2 hours later, it's at a final position, and it's 50 kilometers east of Dauphin. How far has the car gone, and in what direction? Okay, so initially it is 30 kilometers east of Dauphin. Here's Dauphin, right? And my initial position, my XI, is 30 kilometers east. Now remember, they didn't drive there. That's just a reference point, D for Dauphin. We are currently 30 kilometers east of Dauphin, and we don't care how we got there. 2 hours later, its final position is 50 kilometers east of Dauphin. Now I'm going to use a different color here. I'm going to use green. Remember, it's of Dauphin again, so it's green, right? Starting from the start there, so that is 50, and that is my final position. How far has the car gone in what direction? Okay, most kids can easily see that the car has gone from right here, we do this in red, it's gone from right there to right there, and so obviously it's gone 20. Okay, that's easy, but it's how do you do the vector subtraction? And always vector subtraction, displacement is final position minus initial position. So it's my final vector, which is my green one, which I'm going to grab here. And I subtract the initial. And that means take this, flip it left to right. Okay, so it's pointing the other direction. You can see the 30 went backwards here. And then I add it tip to tail, like this. And so my end up resultant, that we already knew here in red, is from where I started to where I ended, just like that. Well, pretty close, right? Okay, so this red one here, that is my displacement. How far has the car gone in what direction? It's gone 20 kilometers east, and that's the diagram for vector subtraction. Let's have a look at number 2. Use vector subtraction to calculate the displacement going from an initial position of 3 kilometers north of Dauphin to a final position of 5 kilometers east of Dauphin. Solve with a scale drawing. Okay, so once again, let's put D for Dauphin in red. My initial position I'm going to do in black. Initial position is 3 kilometers north of Dauphin. 3 kilometers north. That's my XI. The final position is 5 kilometers east of Dauphin. Final I will show in green again. Remember, of Dauphin, so this is my XF. It is 5. Solve with a scale drawing. Now that's not a picture showing vector subtraction. To show vector subtraction, we have to flip. So remembering that always displacement is final minus initial. Okay, so I take my final vector, my green one, my minus xi, so I have to take this one and I have to flip it upside down. Let's do it this way this time. And add it tip to tail, just like that. And now my resultant is from there to there. It says solve with a scale diagram. You probably should use a ruler and a protractor. You could obviously also say if this is 5 and that's 3, you could also say that your displacement squared is going to be 5 squared plus 3 squared, and you can work that out for yourself. The angle here is going to be the inverse tan of opposite over adjacent, 3 over 5. And you can check the answers to see what the actual answer is. All right, so that's number 2. Let's continue with number 3. Find the magnitude and direction of the displacement involving going from a position of 4 kilometers west to a final position of 4 kilometers south. Now, it doesn't say of Dauphin here. We can assume it's of Dauphin if we want. It can be any old town at all. It doesn't really need to be. I've sort of, extended the question a little bit here. So let's just have a look. Final position is 4 kilometers south. Let's start with our initial, I guess. 4 kilometers west is my initial. XI. Final position is 4 kilometers south. XF. Once again, displacement is final minus initial. So I take my final, I flip my initial around, add them tip to tail. There's my displacement. Once again, it doesn't say scale drawing here, so we could just go d squared is equal to 4 squared plus 4 squared. D is going to be the square root of 16 plus 16, square root of 32. Giving you an answer of 5.7. And the angle, again, is this one here. Inverse tan, this is going to be 4 over 4. I'm hoping you should realize you don't need a calculator for this. Okay, if it's 4 over 4, then that's going to be 45 degrees. In fact, that's going to be south, 45 east. I think you get the hang of it now. I'm hoping I don't need to do number 4. Let's move on to some of the harder questions. This one here, Lisa's flying an ultralight aircraft with a maximum speed of 20 kilometers an hour. She sets her course at a bearing of north 15 west. She flies for an hour at the maximum speed and ends up 8 kilometers bearing north 8 west from her start point. What was her resultant velocity and what is the wind's velocity? So there's actually 2 questions here. We're first asked for her resultant velocity, okay? Now we know that she's actually flying at 20 kilometers per hour. She sets her course at a bearing of north 15 west. So that's the plane. The plane vector is north 15 west. She flies for an hour at her maximum speed and ends up 8 kilometers at a bearing of north 8 west from her start point. What was her resultant velocity? Well, she ends up north 8 west, so her resultant is some speed at north 8 west. What speed did she go? She flew at 20 kilometers an hour, right? But she had the wind affect her somehow. So how are we going to find out what her actual maximum speed was? Well, she ended up 8 kilometers away and she flew at an hour, right? So her actual speed is 8 kilometers divided by 1 hour. Her actual speed is 8 kilometers per hour. That is her resultant velocity, okay? So resultant velocity is 8 kilometers per hour at north 8 west. Do we know the plane speed? Yes, we do. The plane speed is 20 kilometers per hour, and that's at north 15 west. What we don't know is we don't know the wind speed. The wind obviously made her fly slower. She could have gone 20 kilometers an hour if there was no wind. She only ended up flying 8 kilometers an hour in a slightly different direction because of the wind. So, resultant is plane plus wind. We are solving for wind. Take it to the other side, and you get the resultant minus plane. We have to take the resultant and subtract the plane. Those are the 2 vectors we have to subtract. So let's go ahead and do that. I'm going to draw my resultant. It's at 8 kilometers an hour, north 8 west. North 8 to the west. And that value there is only 8. We're going to need a scale here, like 1 centimeter equals maybe something like 2 kilometers per hour. So that is my resultant. And now I have to subtract the plane speed. Now the plane was 20 at north 15 west. So 20 at north 15 west. This is my plane. This is my resultant. I have to subtract them. The way to subtract them is to take this, flip it around. So it's actually going to be south 15 east. And then I'm going to add it tip to tail to this one here. Something along those lines. Now obviously I haven't used a protractor here or anything, so my angles might be off. Certainly my scale is quite a bit out here, but you should have something along those lines, and then your actual wind speed is going to be from where you start to where you end up. That's your wind speed. And you can look on the page to find the answer.